This video is about Lean, the Lean prover, which is used to prove mathematical theorems formally. So, Lean prover is actually a fully fledged functional programming language, but in this video, we'll try to understand how the type system works in Lean. Of course, we won't cover the full type system, but we'll only get a simple introduction. So, first of all, you should install Lean. Before installing Lean, you should know that the version of Lean that is used currently is the Lean4 version. There used to be a Lean3 version, but that is kind of deprecated, so you should use Lean4. Now, to install the Lean, you can go to this site, which is basically the Lean Provers community site, and here you can go to installation in Get Started. Now, there are actually several versions. You can do Lean in online too, but I prefer using the thing in my computer. And you can follow the instruction in the official Lean manual. So if I go there, I'll open this in a new tab, and there. So here it says it gives instruction of installing Lean via VS Code. Now VS Code will be necessary because the plugin used in Lean, that's actually must to use, but we won't. I would suggest not to install via VS Code because I prefer installing the actual binary and maintaining that. So you can actually go to the setup for that, and here you will find the extended support notes, like how to install Lean. Typically you will get 3 binaries when installing Lean. One will be eval, which is used to manage the versions of Lean. So Lean has a quite a regular release schedule. So there's like currently, I don't know, probably Lean 4.17 is live, but in a couple of months maybe another version will come. So to manage all of these, you use Lean. Then there's a Lean binary which you can use, and then there's the lake. Lake is the binary that is used to manage Lean projects. So it's kind of like npm for Node.js, lake for Lean. Now using lake, you can create projects. So in fact, I have done that already. I have basically used this command, lake init the project name, to create a project, and I'm gonna show you in that project. Another thing that we'll need is basically a plugin called the Lean4 plugin for VS Code, because Lean is actually an interactive system. Like to work with the Lean, you will definitely need interaction, like the visual information. For that, you will need the plugin definitely, because without the plugin, it's quite a pain to work with. So I'll open VS Code. So in VS Code, I have already installed the Lean plugin, and I have run lake init to create a project. So it has given me this structure. In particular, if you look at this Lean toolchain file, you will notice that this project is working with Lean version 4.17. So all of these are not necessary for us, but the main thing that you need to notice is that there's something called main.lean, which is kind of the entry point, and it is importing another file. So in Lean, you can import stuff. If you click here, you will go to this actual file, which is the Lean for YouTube Lean, which is this file, and here's another import. And if you click here, this takes you to the basic.lean file. So basically, I'm going to create another file here called scratch.lean, because I'm going to show stuff here, and we're going to work here. So let's start with what Lean is. So this is how you can write comments. So Lean is a functional programming language. So if you have idea about functional programming language, I think that would be the best. Functional programming languages are a kind of a paradigm different from object-oriented language. So in functional programming language, the idea is that everything is kind of a function. Not everything, but most of things, almost everything is defined in terms of functions. But we're not going to jump deep into the functional programming language paradigm right now. Instead, we're gonna see simple usage first. First of all, let's see how to define variables. So in Lean, you can use the keyword def and then the variable name, and then you use colon equals and then the value, like 1. So this is a variable that is a, which is value is 1. We can also define other kinds of variable like b equals true, which is a boolean, or you can also define c, which is string, or you can define d, which is integer. Now all of these are variables. Now there's a little bit of a problem because unlike OOP languages where variables can never change their value, variables can change their value. A functional programming language like Lean does not allow that. So in Lean, variables are immutable. Variables are immutable. So once I've defined A, I can never say something like A equals 2. No, that's not possible. Okay. Another thing is you will notice that I didn't specify type information. Now Lean is strongly typed, so we can actually specify type information like this. We can say that this is a nat. Nat means a natural number, so which is basically 0 and any positive number. We can say this is a bool. Sorry, this is a bool, which is true and false. We can say this is string, and we can say this is an int or an integer. When we did not specify this, Lean understood that okay, the type of 1 is nat, the type of true is bool, the type of hello is string, type of -1 is int. But it's a good practice to, I believe, to specify the types. Now, after creating variables, the next thing that you can do is create functions. I know that's a bit of a jump, but it's functional language. So now we're going to define some functions. So the way to define functions is also uses the same keyword, the def, and then the function name. Then we're going to need to add the parameters. So I will say that f takes an x as an argument, which is of type nat. So this is how you say that f is a function that takes natural number x as input, and then it will return something. So I will say it returns 2 times x. So in functional languages, function bodies are always kind of a one-liner. That is, there are always some mathematical form. Well, not mathematical, but there's some formula. So f here takes x and returns 2 into x. Now this is a function that takes a natural number and returns a natural number. We specified that it takes a natural number as an input, but we never specified that it returns a natural number. Lean deduced it, but we can actually write it like this. So after the colon, we can say, okay, this is the return type. After the colon equals, this is basically saying this is the definition. We can actually apply this. So we can define another variable, which is equals to f3. So what is this is saying that e, the value of e is f applied on 3. So is another shocker that in Lean, we don't write something like this. No, we don't write like that. Instead, what we write is basically f and then a space and 3. That just means f is being applied on 3. So by definition, f takes x and returns 2 into x. That means f is going to take 3 and return 6. So e's value is 6. Now, how do we see this? We can like print the value of e, but that is actually the function, programming language way. We're not going to focus on programming language. We're going to focus on the proof, the interaction with Lean. So to interact with Lean, you can use the Lean4 view. That is due to the plugin, like the Lean extension. Due to the Lean extension, there's a button like this, Lean4. When you click on this, there's something called info view, toggle info view. You can also Control Shift Enter on Windows, I believe. So when I click on that, it opens up a side panel, right? So this side panel has information about your file, and two good ways to get this information are via Lean commands. So one Lean command is check. So hash check, and after hash check, you can put any expression of value, for example, a, and this will basically show in the right side what is the type of the expression. Now, due to having another expression called irrelevance, this is also showing up here, but generally without irrelevance, this won't happen to you. You will have to look at the right side. So A's type is natural number. Okay, let's check others. For example, what is the type of B? B is a bool. Okay, let's check something else. What is the type of C? C is a string. And as usual, what is the type of D? D is an int. You can also check type of functions. So what is the type of F? F is a function that takes X as input and returns a natural number. So this is how Lean is showing me that this is a function. There's also something called eval, which basically evaluates values. So when I say something like 2, it evaluates that 2 is 2. But use something else like 2 plus 2, which is 4, or 2 into 3, which is 6, or 2 to the power 50, which is this big number. So notice that Lean has exponentiation built in, and it also uses arbitrary length numbers, I believe. So you can increase this to like 100, and it will show you that too. But of course, Lean is not meant to be used for this. It's not meant to be a high performance language. It's meant to be used for mathematical proving. Okay, and we can also do like F5. So Lean is basically unfolding the definition of F, that it takes X and returns 2 into X. It's doing that in 5 and saying, okay, so this must return 10. So you use check for checking the type, and you use eval for evaluate. Now eval will not always work, because there are some things that are declared as non-computable in Lean, and for those non-computable things, eval will actually fail. But we will see example of that in future. Okay, now so far I have only shown you one way to define function. There are actually several different ways to define function, and I'll show you them. And I'll also show a different thing, and that is Unicode symbols. So first I will say F, and I want to say this is F sub 1, like the mathematical how you say subscript 1. You can do that in Lean. You can do that thanks to the VS Code extension. I can say slash 1, and that becomes subscript. So F1 is a function that takes X as a natural number, and it returns a natural number which is equals to 2 into X. I can define the same function as F sub 2. Notice that I wrote slash 2 to get the subscript 2 as like this. I will say directly that I will define it directly. It's going to be defined as, I believe you call these lambda functions in other languages. Fun X, this symbol 2 into X. So this is basically saying that F2 is the function that takes X and returns 2 into X. Now notice that this, when I hover around, it says X as a natural number. So this is also a behavior of Lean. Lean is saying, okay, so it's X is something that you can multiply with 2, and one way to multiply 2 is basically natural number multiplication. So that's why it's using natural number as type of X. You could actually specify the type like X colon nat. That would be strictly specifying it to get the 2 into X. There's another way. You can say def f3. Now I'm going to use something called lambda symbol. So the lambda, I write slash lambda and it's lambda. There's actually a shortcut. You can say lam and then tab, and that also matches to lambda. Basically, it will match that the lamb is the prefix of lambda. So lambda, which takes X and which returns 2 into X. So this also defines the same function. So F1, F2, F3, these are all kind of the same function. And in lambda notation, you can also use xnat to define the type of the input. There are also two more variations. Like in both this fun case and in this lambda case, you can actually replace this arrow symbol to slash maps to, right? Or a shortcut slash map tab to get maps to. You can also replace that here, slash maps. Okay, all of these are same. Now let's check the types. So first let's check the type of F1. F1's type is X natural number and returns natural. Simple. Let's check the type of F2. F2 is also same. It takes a natural number. F2 is also same. It takes a natural number, returns a natural number. Let's check the type of F3. F3 is also same. It takes a natural number, returns a natural number. But we could actually have defined the types in a separate way. So in case of F1, there is not really any place to define type of F1. But in case of in case of F2 and F3, you will notice that they are kind of like normal constants. So when you had defined something like def a as 1, there's a place before this colon equal operator. We could say a nat to define the type. We can do something similar for this F2 and F3. We can say F2 is a type. The type of this is written like this. It takes a nat and it maps them. So there's, we can do /r to net. So this symbol is basically a symbol of mapping function. So f2's type is something that takes a net and it returns a net. And after I wrote this type, you'll notice that the check output has changed. F2 is now written as something that takes net, returns net. F3 is still written the old way, but you can also change the type of that. We can say F3's type is net, that maps something that maps net to net. So F3's type has also changed. So this is kind of more mathematical way to say the type of F3 is something, a function that takes a net and returns a net. Okay, next, these are, so far I have only defined single valued functions. There are multi-valued functions. We can define a multi-valued function as something like this, something that takes x as a net, and then it takes another y as a net, and then it returns x plus y. So this is a multi-valued function. We can write this as you check the type of G, then you will see a shorthand notation. Xy could be collapsed to one bracket. In fact, we can do that here too. I can collapse this to one bracket. We can evaluate this. Eval G1, 2. So G1, 2, you get 3. We can do G10, 10, 20. We get 30 as usual. But one thing is, it's almost done in every functional language. That is, we can do something called currying, which basically is that when you have functions that are multi-argument like this, which takes one x, then one y, and returns x plus y, these are not really multi-input function. Rather, these are a function of one input that returns another function. What do I mean by that? Let me define G in another way. I will use G apostrophe. So notice that I can put apostrophe in name and Lean. So I will define like this. G prime is a function that takes one natural number, it returns another function. So this is one way to define G. I actually need to define the types. So Lean can't actually figure out the type here, so I'll actually have to provide the types. I can actually provide the types here like this. Yes, this is enough. So Lean knows that x is a natural number and we are using x plus y. That must mean y is also a natural number. So notice this, that this G prime is actually the same as G, but notice how it's defined. G prime is a function of x that is returning another function of y. So when we check for G prime, we see that G prime is taking one x as a net, one y as a net, returning net. And when you do check for G prime and 10, that is a function. So G prime 10 is basically a partially applied function. We still haven't applied the y yet. So that's why you still have the G prime 10 is basically a function which still you can still use that on another natural number to get another natural number. In fact, you can also assign them to another variable. So I can say, okay, def h is same as G prime 10. So what is h? H is basically a function that is taking one natural number and returning another. Or it's basically a partially applied version of G prime. We have applied the 10, but we still haven't applied the y yet. So we can do eval h20. So h was already partially applied, 10 was already applied. After applying 20, we get 30. So what the ultimate point I'm trying to make is that functions in multi-argument functions in Lean are basically curried function. That is, they are a chain of inputs. So when you have something like this, that def f has a, b, c, d, e, all are net and returns a net, something like this, you can apply this function to a certain prefix. So you can say like, okay, so I can apply it to f1. That's still a function that needs 4 arguments. I can then do 2. That is still a function that needs 3 arguments. I can apply 3. That is still a function that needs 2 arguments. Then 4. It still needs 1 argument more. And then 5. To finally get the final result. And so you can do eval on f1, 2, 3, 4, 5 to get the value of 15. But you can't actually do eval on any of the partial applied version, because then eval will need to show a function and it does not know how to do that. Okay, enough about function. But so far you will have noticed that we have seen how to define variables, how to define functions. One important thing you have noticed that we have seen several types. So what types are there in Lean? So we have seen the type nat, we have seen the type bool, we have seen the type int, we have seen the type string. The most important thing about Lean is that these types are also something that you can work with, meaning you can not just work on the natural numbers, but you can work on the nat type too. So in fact, we can check with them. Nat is a type. Basically, nat also has a type, right? So when I have checked for one, you will notice that one had the type nat, but the nat object itself has the type, right? Similarly, when you had checked for true, true has the type bool, right? But we can also check what is bool. Bool has a type. So in Lean, types, the type system is not really terminating, in the sense we can't really stop at the nat. Nat has a type called type, and that type also has another type, right? We can write something like this. You notice that the object type also has a type which is type 1, right? And we can go even further. What is that type 1? Type 1 has type 2, and type 2 has a type 3, and type 3 has type 4. So you can see I'm creating an inception of pop-ups. Anyways, so in Lean basically we have a hierarchy of types, and this hierarchy is actually implemented as something called sort. So there's something called sort 0, then there's something called sort 1, then there's something called sort 2, then there's something called sort 3, then there's something called sort 4, and so on. And all of these have the type that is next, meaning sort 0 has type sort 1, sort 1 has type sort 2, sort 2 has type sort 3, sort 3 has type sort 4, and so on, right? So this is creating an infinite chain of types. Now for ease of working, Lean doesn't really try to expose this sort naming, but it defines a new naming. In Lean, sort 0 is said to be prop. So instead of writing sort 0, we'll write prop. Sort 1 is written instead as a type, which can also be written as type 0. Sort 2 can be written as type 1. Sort 3 can be written as type 2. Sort 4 can be written as type 3, and so on. So in Lean, when we'll be working, you will see that Lean will expose not the sort names, but these right names, the right hand side names: prop, type, type 1, type 2, type 3. The reason for this is that prop type is actually special. We'll see this in the future, that prop type has special exceptional properties. Anyways, so we can write this, so we can check. So what is sort 3? So notice that sort 3 has checked for sort 3, but it wrote it as type 2. Like I said, sort 3 is type 2, and sort 3, which is type 2, has the type 3. It's a bit confusing to wrap your head around, but this mapping is the most important thing. Now, what were these? What were these nat? What were these bool? What are string int? What were those? Let's also check that. Nat is a type. Remember, type is just nothing. Type is just sort 1. What was bool? Bool was also a type. What was string? String is also a type. So all of these are types. Now you might ask, okay, so I have so far learned about a chain of types for these sorts, and then where are these nat and bool and string coming from? We'll know about those later, but just know that every type in Lean is somehow coming from this chain of sorts. Every type. So we have the chain prop, which is of type, which is of type 1, which is of type 2, and which is of type 3, and so on. And in this chain, there's also nat. So I'm writing those below. So like nat, int, bool, string, all of these are actually like have type. So every type in Lean is coming from this chain. How are they coming? There are actually three ways. So types can be the source directly. Types can be one of the source directly. Types can be a function type. Function type. What is function type? Remember, we had written something like nat / nat. This is the type of functions that takes input nat and returns nat, right? So these are function types, or they are inductive types. So inductive types are kind of like classes from OP, but it's not different. And this nat, int, bool, string, all of these are just inductive types. How inductive types work, we'll see that probably in the future. Just know that any type that you face in the Lean, it is either a sort, or it is a function type, or it is an inductive type, or a combination of these. All types are coming from these three things. Now, what about something like 1? Is this also a type? Like I can write, I have like 1 type is nat. Is there something that has type 1? No, because 1 is not a type. 1 is a object. Not an object. 1 is a kind of constant. So when I said that all types come from these three things, all object time come from 4 things. So in Lean, all objects are either sort, basically another type, or they are function types, or they are inductive types, or they are constants. So all objects in Lean are either a type, in which case they come from these three things, or they are direct constants. So 1 is a constant, 2 is a constant, and so on. So these constant, how these constants are coming, they are actually coming from the inductive types. Again, we'll see those later, but just know that all objects in Lean are one of these 4 things. Okay, now one last thing, I said that Lean, you can work with types just like you can work with natural numbers or integers, right? So in fact, I was able to define a function that takes a natural number x and it returns a natural number by like 2 into x. You can do something like similar with types themselves too. So you can define a function as g, which takes a type as input and then it returns another type as input. For example, you could say whatever type you return, you send in, you will always get nat. So that means you can check something like you can evaluate something like g of bool. Well, eval is not working, but we can really understand that no matter what type we input as t, we're always gonna get nat, right? So we can actually do a check, and we'll see that the type of g bool, g applied to bool, that is type, but from the definition we know that g of bool is basically nat. We can probably do something like this, I believe. No, that won't work. Yes. So basically we can define function types too. I will define another function, def h, t as a type, and it will return a nat. So notice that the function can actually crisscross around the types. I will define it as just define as constant 2 for now. But notice that int itself takes as an input which is type, but it returns a nat. So if you remember that hierarchy, nat has type, but t, which is of type, that has type 1. What I'm basically trying to say is that So far we have seen functions which take the a type and return a type of the same level. But this function h, it is taking a type of one level up. It's taking a type of type 0 and returning a type of nat. Nat is kind of one level down from type 0. So that is why I'm saying that you can crisscross the types in functions. You can actually define more complicated functions. For example, I would say something like this. If t equals no, let me define something else. Def h as something that takes a natural number and returns a type. Let's define it something as if x equals to 0, you will return nat, else you will return bool. So notice that depending on x, I'm returning a different type. I can return a nat or I can return a bool, depending on whether x is 0 or not. So I could work with h0, which will basically just evaluate to nat, or I could work with h2, which will evaluate to bool. So this is why I'm saying that functions, you can treat types as if objects in Lean4. Okay. Now, the most important thing to remember, I would say, is that the type hierarchy, because we will see more of that in the future. But overall, this is like the most simplest part of type in Lean. There are more complicatedness, like there's inductive types, there's dependent types, all of that. We haven't touched any of that, but I think this is a good way to start. Thanks.